Let me thank you again for having me here. And Colin is right that I'm interested in parasite conservation, and that's what I'm going to talk to you guys about today. Let me start off right up front by saying I know that most of the folks on this call work on human diseases, and I want to assure you that I am not at all in any way, shape, or form advocating that we worry about the fate of human diseases. I think that they should be destroyed, annihilated, controlled in any way, shape, or form. What I'm going to talk about today are wildlife parasites, which is my primary stock in trade. And before I start in, I want to begin just by making sure that you know that I didn't do the work that I'm about to tell you all alone. Lots of people were involved in this project, and the work was supported by the Alfred P. Sloan Foundation and the U.S. National Science Foundation, along with the University of Washington. And I want to make sure to give my heartfelt gratitude to the curators at the 14 museums who allowed us to work on their specimens. Okay, so ecologists, I'm one. We've been obsessively documenting the decline of biodiversity since the field was invented. It's our favorite thing to do. There is nothing that we love more than counting things as they nosedive into oblivion. You can take, for example, the insects, for whom biodiversity has been in free fall as a result of land use change and the intensive use of insecticidal agrochemicals. Or the plight of amphibians, which have been decimated by a global epizootic of chytridiomycosis, a fungal infection. Birds haven't been faring well at all, primarily due to habitat loss. And many mammal species are on the fast track to extinction. And we've done a really good job of tallying all of this up for so many species. Of course, we all care about the plight of panda bears and pretty birds and even adorable frogs. And we've gone so far as to do these tallies for icky things like insects. But parasites are just beyond the pale. We have literally not the foggiest clue about how populations of wildlife parasites have been changing over time. And I think that's for two reasons. One is that they're gross and no one cares about them, with the exception, of course, of all of us in this Zoom room. And there's also very little incidental information that's passed down to us from decades ago, because there just aren't a lot of circumstances where people have been recording parasite data over long stretches of time. Butterflies, sure. Panda bears, yeah, but parasites, no. It's really important that we figure out what parasites have been up to over the past couple of decades, because for one thing, it sure seems like we're seeing more outbreaks of parasites recently than we did in the distant past. Think about something like sea star wasting disease, which affected the west coast of North America in 2013 and turned sea stars into literal piles of mush. It even drove one species, the sunflower star Pycnopodia, to the brink of extinction. And if parasites are increasing in abundance, we need to know so that we can anticipate events like this one. On the other hand, we might want to be on the lookout for parasite declines, because parasites are species just like any others and could be nosediving just like insects, amphibians, birds, and mammals. In fact, by conservative estimates, parasites are 40% of all animal species. But parasites aren't just diverse, they're also critically important components of ecosystems. Consider Carpinteria salt marsh just south of Santa Barbara in California. This tiny marsh used to be a parking lot. It was restored a couple of years ago, and if you go into this marsh and weigh and measure everything that lives there, you'll find that all of the parasites in this marsh weigh about as much as a small herd of elephants. No ecologist in their right mind would think that putting a herd of elephants into a marsh as small as Carpinteria would have zero ecological influence. These parasites are just as powerful as a bunch of elephants, but because they're hidden inside of their host, that power is really easy to overlook. So parasites are ecologically important for better or for worse, and yet we have just no clue what their trajectory through time might be. My goal is to fix that. My team recently took a stab at this problem, and you can read the details in our recent publication in PNAS. Now, I mentioned that there just aren't data on wildlife parasites and how they've changed over time. So how did we get these data? Really simple, museum specimens. When vertebrates or invertebrates are preserved in ethanol or formalin, their parasites are preserved right alongside them. And a simple parasitological dissection gives you all of the metazoan parasites that occurred in a host at the time of its death. It's not rocket science, but nevertheless, it's really powerful. It's the only way we currently have to reconstruct trajectories of parasite abundance at the scales that we need to test whether the world is wormier than it used to be. For this project, my team focused on Puget Sound, which is a big inlet of the Pacific Ocean and the second largest estuary complex in the US. We picked it because we're located right here. Home seemed like a good place to start. And our university's museum, the Burke Museum of Natural History and Culture, has outstanding representation from this region. We were able to get enough specimens to evaluate change over time in the parasite burden of 8 fish species. And these were chosen to span a variety of trophic levels and body sizes so that we would maximize the diversity of parasites that we would find. We were able to source most of these specimens from the UW fish collection at the Burke Museum, but we did supplement from 13 other collections as well. And for many of these parasites, we were able to get back into the 1880s. These specimens are literally parasite time capsules passed down to us from decades ago, and we use them to ask both how and why parasite abundance has changed over the past century. This question would have been impossible to answer without the massive data set that we assembled. In total, we counted 17,259 individual parasites in 699 hosts. Our time series stretches from 1880 to 2019, but the vast majority of data are from 1920 onward. And that gave us 85 parasite taxa, making our data set the largest long-term data set of wildlife parasite abundance ever assembled. And here's what we found. On the y-axis, we have each of our 85 parasite species, and they're organized by the kind of life cycle that they have. Some parasites have just one obligately required host species in the life cycle. We also call those directly transmitted parasites. We had 20 of those. Other parasites need 2 host species to complete the life cycle. Some require 3. On the x-axis, I'm going to give you the random effect of year for each parasite species. So parasite species that are positive on this x-axis are increasing through time, and negative are ones that are decreasing through time. And so what you can see from this plot is that there are some parasite species making major gains through time and some experiencing major losses. But if you look at the groupings, you'll find about even positive and negative responses among the one-host parasites, about even positive and negative responses among the 2-host parasites, and then a tendency toward decline among those parasites with 3 or more hosts in their life cycles. I also want you to note that these guys, the ones with the most complex life cycles, are 52% of the species that we found. And if we generate a prediction plot for each of these groups, this is what it looks like. Directly transmitted parasites in yellow and complex life cycle parasites with 2 hosts in their life cycle in green don't really change over time. But parasites with 3 or more hosts in their life cycles plummet. The scale of the decline is pretty enormous. It's 11% per decade, which is greater than the magnitude of decline that's triggered conservation action for things that people actually care about, like birds and mammals. So this is a massive, previously undetected loss of parasite biodiversity. But why is it happening? We not only wanted to know how parasite abundance was changing over the past century, but also why. Luckily, we had a pretty fantastic data set of environmental parameters for Puget Sound, and we were able to build some statistical models to figure out which of these environmental variables was most closely correlated with the declines that we observed. Let's take a look at the slope of the relationship between each potential driver and parasite abundance. On the x-axis, we have year, sea surface temperature, 2 principal components for pollution, and host density. And we already knew from the previous analysis that the relationship between time and the abundance of 3 host parasites is negative. We found that the 2 pollutant principal components and host density not associated with parasite abundance in any direction, but sea surface temperature was associated with parasite abundance, and the magnitude of the effect was very similar to the effect of year. In fact, we found that parasite abundance declined with increasing sea surface temperature at a rate of 38% for every 1 degree increase in temperature. And that's a little bit less than the amount of warming that Puget Sound has seen since 1950. So what's the upshot? First of all, the loss of parasite biodiversity that we documented is massive. Puget Sound is a lot less wormy than it used to be. And of course, this is just a correlational study. We can't be definitive about causes, but of the potential drivers that we screened, climate change seems to be the most likely culprit. And I know what you're thinking right now. Finally, a silver lining to climate change, good riddance, we never needed parasites anyway. Maybe not. Parasites are species. There are a lot of them. They do things in ecosystems. I would argue that their disappearance might not be the best thing, despite our general distaste for them. And your next question is probably, this is happening in Puget Sound, is it happening elsewhere? My answer is I don't know. Our data set is, for the moment, totally unique, but we are working on several new data sets. So we'll soon know whether this climate-driven parasite decline is general and what other factors might be shaping parasite populations in a changing world. The historical ecology of parasitism, this use of parasitological dissection of natural history specimens, this is the lowest of low-hanging fruit. It's cheap, it's easy. There's a museum within a couple of miles of you right now holding these parasite time capsules. Natural history collections are the only way that we're ever going to know whether the world is getting wormier or not. Thanks.